So we just saw how with the Clapeyron equation, we can understand, or the Clapeyron equation gives us insight into how the phase boundaries between different phases are affected by pressure and temperature. Okay? And so what we could do now, or what we're going to do now, is we're going to make further assumptions in order to simplify the equation down into something that we could use to estimate things like the enthalpy of vaporization, or get an idea of how to measure the enthalpy of vaporization for a given chemical based on its pressure and temperature transition values. Yeah. All right, and so to do that, we're going to develop what we call the Clausius-Clapeyron equation, or the Clausius-Clapeyron approximation. Okay, and so this approximation we're going to develop, this is relevant for if we're going from the solid or liquid phase to the vapor phase. And what this approximation assumes is that, one, like I mentioned earlier, that the molar volume of the vapor phase is just so much larger than the molar volume of the solid or liquid phases. Okay? Therefore, if we took a look at delta V, which would be either the vapor minus the solid value, or the vapor minus the liquid value, because the vapor value is so much larger than solid or liquid, essentially this delta V is just the V sub V value. Okay, that's the first approximation. The second approximation is that we assume that the vapor acts as an ideal gas. And so what that would mean is that our molar volume, V sub V, molar volume of the vapor, we could estimate it just using the ideal gas law. Okay? All right, and so with those assumptions in hand, let's go back to the Clapeyron equation. Constant delta G. This is equal to delta S of the liquid to the vapor phase over delta V of the liquid to the vapor phase. Okay? And so if you remember from our discussion on the temperature dependence of delta G, we saw that this delta S, we saw this is equal to delta H over the transition temperature, which I'll just call, for the purposes of this exercise, just T. Okay, so the liquid to vapor transition is delta H vap. Okay, all right, and then if we assume this is an ideal gas, this is just RT over P. And so this slope of dP dt at constant G just ends up being approximated as this, T squared. Okay. All right, and so let's now rearrange this equation so that we have T squared over P dP dt delta G, which is equal to delta H vap over R. All right. What we should notice on the left-hand side is a couple of things. And so we have this partial derivative, right? But what we have here is essentially dP over P. So notice that we have 1 over P dP. And that is essentially just the derivative of the natural log of P. And the other thing we should notice is that we have what you could write as dt over 1 over T squared, right, if you kind of rearranged it. Or, in other words, if we write it like this, we have this in our equation, and this is equal to this, right? The derivative of 1 over temperature, if you do the chain rule and stuff, it gives you this. All right. Okay, and so what we could do is we could rewrite our partial derivative like this. Is equal to negative HVAP over R. Okay? And so when we make these approximations, what we get is known as the Clausius-Clapeyron equation. Okay? And so graphically, what this equation is describing would be if we had the natural log of pressure and plotted it versus 1 over temperature, whatever sort of function we would see, the slope of that function would correspond or would be related to the enthalpy of vaporization, which is something that we may want to know. Okay? And so that's how this equation can be used as a model for allowing us to determine delta HVAP from experiment, or vice versa. If we knew HVAP, we could then calculate what the phase boundary would be between the liquid and vapor phases, or the solid and vapor phases. And so this is a form of the Clausius-Clapeyron equation. But a lot of times, people kind of take it one step further. So they make another approximation, sometimes. Okay? And what they do is they assume that over a temperature range that they're interested in, that the enthalpy of vaporization is going to be a constant. Okay? And so if they assume that that's constant, what they then do is they split up that partial derivative into like a separable differential equation. R d 1 over t. Okay. And when they do that and integrate it out, they get this. Okay. All right, and so this is another form of the Clausius-Clapeyron equation. And one that if you measured the transition pressures at one temperature and another temperature, you would be able to figure out the enthalpy of vaporization. Okay? Furthermore, people can rewrite it like this. So a general form would be the natural log of P is equal to A minus HVAP over RT. This is the version that you would get if you just took like an indefinite integral, where A would be some constant. And of course, the temperature here has to be an absolute temperature. All right. All right, and so these are the various forms of the Clausius-Clapeyron equation. It's good. It gives us insight into, how the phase boundary between two phases, between liquid and vapor, or solid and vapor phases, are affected by temperature and pressure. But, a lot of these assumptions that we're making are kind of restrictive. Like, for instance, that HVAP is unaffected by temperature or pressure, or that we're dealing with an ideal gas, right? So a lot of times these assumptions aren't really good assumptions, and so the Clausius-Clapeyron equation isn't that accurate. And so sometimes what people resort to is they resort to models, what we call empirical models, so things that aren't derived from like the original thermodynamics equations. Rather, they kind of just resort to models where they just fit data, get experimental constants, but don't really have a good reason for the value of those experimental constants. But in any case, these equations, are fairly robust, and they're good for just being able to estimate what like vapor pressures would be. Okay, and one such example of that equation, of an equation like that you've already encountered in MEB2, is the Antoine equation. Okay, where your vapor pressure, natural log of the vapor pressure, or P sat, is equal to A minus B over T plus C. So this kind of looks like the Clausius-Clapeyron equation, because you have an A here, another constant here, but the temperature term in the denominator here, instead of just being temperature by itself, it's added onto it is another constant. Okay. So, you could see the Antoine equation in natural log form, or more commonly, you'll see it in log base 10 form. So, I'll put a prime here just to indicate that if you change between natural and base 10 log, you'll get different constants.